Hello and welcome back to another episode of TACHES Teaches. I'm Tash, and in today's video I'd like to talk about Bernoulli Gates. What I'm about to show you is my interpretation of a Eurorack module called Branches by Mutable Instrument, which basically allows you to take a gate signal or audio signal and decide whether or not to send it to either output A or output B via a probability coin toss. If you have a bias in favor of output A, you are more likely for that signal to go out of output A than output B, and vice versa. If you have it somewhere in the middle, it's equally probable that you'll get an output on A as B. But I'd like to show you how you can implement that without having to buy lots of Eurorack modules within the grid to get some rather interesting, but at first simple ideas that then branch out and you can have a lot of exciting chance-based fun with it. So without further ado, let's jump right in. I think a nice visualization for how a Bernoulli gate works is to take a gate signal and feed it into two separate oscilloscopes. As I press play, you'll see that we're getting an identical gate signal being sent through both. And if I unhook one of them, it's now just on one, and if I unhook the other, it's now just on the other. So what a Bernoulli gate does is it allows us to take one signal and through a coin toss or a chance decision, decide whether to output that signal to either 1 or 2, A or B, top or bottom. And the way that we can do this is by taking a split module. And we're basically going to split this gate signal into the top one going to this oscilloscope and the bottom one going to this oscilloscope. If I now press play, you'll see that all of the gates are going through the top. And because we only have two options here, we're going to set the interpolation to nearest. And that means that if I were to take a value knob, for example, and I were to then take this to just above 50%, if I take it to 49.9, we're not getting anything. But as soon as we get to 50%, we've now shifted over to the bottom output. Or, for example, we could use a button, and when I turn the button on, we're now getting all of them going to the bottom. But how can we do this so that there is a possibility that it will go to the either top or the bottom? Well, we can take a chance module, and this in and of itself is a coin toss defined by a percentage. So if we were to take the output of this chance module and put this into the select in, still nothing will happen because we haven't fed anything into the chance module to decide when it should flip the coin. And if I now take the same gate signal, that means for every one of these gate signals, which are then still being fed through to one of these two oscilloscopes, every one of these gate signals would either send no gate or a gate. And if it sends a gate, it will flip us to the bottom output. And if it doesn't send one, then it will stay on the top output. So if we have a look now, you'll see that we're getting a 50% or equal distribution of gates being sent to both the top and the bottom oscilloscope. And like true randomness, sometimes you'll see a huge number of just going through on one or, huge bits of silence on the other. And I think as humans, we're trained to believe that randomness would be 1, 2, 1, 1, 2, 1, 2, 1, 1, 2. But oftentimes in random, you'll get 1, 2, 7, 1, 0, 0. Fantastic. Anyway, so why is this useful? Well, one of the best things that we could do with this to better illustrate what we're using it for is I've got a kick up here, and I've got a short hat that I've made here, and a long hat here. And I'm going to take the outputs of these oscilloscopes, which is pretty much the same as taking the output of here, but at least we can see it as it's happening. And I'm going to feed that into the envelope for the short hat. I'm going to feed that into the envelope for the long hat. And as I now press play, we're now getting an equal distribution being sent to either the short hat or the long hat. As I start to bring this percentage down, we're now getting only short hats. As I bring this all the way to the top, we're now getting only long hats. And of course, 50% is that equal distribution. But if we start to bias this slightly more in favor of the short hats, we're now getting far more short hats than we are long hats. But there is still the possibility of every gate here that there will be a long hat. Now this sounds okay, but it's still not massively interesting, and that's because it is totally random and it's not quite as appealing just being straight eighth notes. So what we could also do is use the same concept of this Bernoulli gate distribution to decide whether or not we're getting 8th notes or 16th notes then being sent into here. And I'm going to do that by taking a merge module, and I'm going to merge both. Let's make this 16th notes now. So currently we have the same thing as before, but just with 16th notes. And I'm going to make one below that's 8. I suppose I could have just copy and pasted that. Again, currently we're now not getting any 8th notes. But if we were to take a chance module, our trusty chance, and make sure that we set this to nearest, and we feed the output of that chance module in, still nothing, because we need some sort of device to decide how often to coin toss. And we could either coin toss with the 8th notes, which means that we'll get sometimes 2 16th notes in a row, or we could use the 16th notes, which will give us a slightly more erratic chance, because there's more coin tosses per second. Totally up to you which one you use, but you can see how this does create slightly more interesting patterns. And if we wanted to bias this more in favour of 16th notes, of course we just bring that chance down. I'm going to bias it a little bit more in the short hat sense as well. Now it's already a lot more interesting. But let's take this concept of the Bernoulli gate and maybe use this on something else as well. Let's bring this back, and let's say that I'm going to separate this out a bit so we've got a bit more room. Let's say that every time we get a hat, we like the length of this envelope, so I'm going to copy and paste that down there and forget about that for a sec. Let's now change this a little bit. Okay, so I like that length and I like this length. Let's bias it all the way for short hats so we can compare it and say, okay, we're going to send the noise out to this envelope as well, and we're going to send the gate to this device. And we've already got our envelope, although I'll take the same. Let's just add it, in fact. Let's just, which one's add? Control. Okay. So we've now got both of these playing. And what we want to now do is decide whether or not this gate that occasionally hits here will then be sent to either this longer envelope or this shorter envelope. So let's take our device again, and instead of now feeding this into the envelope, we're going to feed that into this split module. We're going to use that signal again for the chance. We're going to send the gate signal from output A into the first envelope and output B into the second envelope. And now we should get, again, another 50% chance, 50%. Okay, that's interesting. And you'll notice that obviously we only have 2 possibilities here, 2 possibilities here, and 2 possibilities here, but they do start to add up. So now let's go down to the longer hat. Let's bias it all the way for the long hat. And we like that length. Let's do something a bit shorter or a bit longer. Cool. Now let's take, what did we use? An add. Yeah, so let's control that in there. And I'm going to take the outputs from these gates, and we'll take the Bernoulli situation again. And I'll take the output of the oscilloscope and put that into the chance module and into here. And then let's use this to decide whether or not we get the slightly longer or the slightly shorter hat. Let's see what we've got now. And what's interesting now is this, if I bias this back to being 50%, means that 50% of the time the gates will go through the top output, 50% of the time they'll go through the bottom output. But when they do go through the top output, 50% of the time they'll go through the top output, and 50% of the time they'll go through the bottom output. So we really do start to build up some rather interesting possibilities here. Let's have a quick listen to what it sounds like now. Let's bias it a bit more in favour of those short hats. Quite interesting. Okay, so that's a great demonstration of using this for hats. In the meantime, I am just going to quickly add, because I think this will add a nice little bit of extra texture. Just going to add a little bit of random LFO, just a tiny bit, to the filter cutoff on these XPs, because I think this will add a really nice bit of movement as well. Let's have a quick listen. Ooh, yeah, that's cool. Okay, now let's look how we could use this perhaps in the context of a melodic part. I'm going to bring all of this up again, make a bit more space for us down below. And let's have a look to see. So if I take a sine wave, my trusty sine wave, by this point you're probably so fed up with its round, warm, bouncy tones, but okay, let's take an eighth note pattern here. And what we've now got a situation of is up above, every time we're sending out a gate, it's going to either one place or another place, but we are therefore getting every single gate going somewhere. Another way that you can use a Bernoulli gate is to send a signal to somewhere or nowhere. So why don't we take a 16-note pattern here again, and I'm going to take an envelope and attach that to the sine wave. And I'm now going to patch that into here and have a quick listen to what we've got straight away. So, okay, cool. So currently, of course, we've just got every single note coming through. It's a bit loud, that. Every single note is going through. But if we take our concept up here again of the Bernoulli gate, and we input that gate in here, and we take the top output to control this, and let's put it fully biased for 0 again. And now every single note is going through the envelope, through this AD. But as I start to bias this up in favor of, say, oh, I'm not actually even going in, that's why. Oh yeah, I'm going into the wrong chance. Okay, there we go. So currently, every single note is going through, but I start to put this to 50%. We're now getting a 50% chance that a note will play. Okay, cool. So what about if we were to take a pitches module, and I'm going to keep this really simple for now, and just set this to 2 notes, and we'll say we've got a C, and we've got another C. So we'll either be doing a C or the octave above. So let's attach that up. And let's say that in order to drive this pitch module, we're going to only move forward when there is a note. So let's attach this up, set it to 2 notes, and take the same gate output from here. So now getting every single note is moving it to the next place. I'm going to bring this down a bit. Okay, interesting. What about only 50% of the time do we get a signal being sent through to the counter? Because that could then lead to some notes not moving on. So let's take the output of that's going into here and input that into the output and take the output there, and we'll use the same output to give us a 50% chance here. So now 50% of those notes that are going through will advance, and 50% will not advance. So let's have a quick listen to that now. Okay, that's fairly interesting. And what about if we were to add maybe a few more notes to this? So let's make this 3, and we'll go for C, we'll do a C, G, and a C. Set this to 3. And now let's have a quick listen to what we get. We could bias this more in favor of it progressing notes, but sometimes it doesn't progress. Okay, that's fairly interesting. Now let's layer this up with something else doing a similar thing. But instead of having 16th notes, let's do everything we've been doing, but let's do this as a Euclidean rhythm. So let's take a clock quantize, and set it to trigger. And let's set the quantize to the 16th note thing. And let's maybe use 11 notes. Let's bring this back up and maybe use a slightly more rolled off tone here. Give it a bit of width. And let's have a quick listen to what we get now. Oh, maybe we could even change the notes. So we've got a C, G, and a C. Why don't we do a G, B, and make it a bigger octave. We'll do a G, B, and an E. See what that sounds like. So now we've got quite a few distributions. Oh, we're on a 3. That's why that's sounding weird. Maybe I could, I'll set that to 3 and go up 1 then. And let's bring a bit of delay in here. Okay, quite interesting. So we've now got these distributions happening. And all of these things could then be biased by setting randomness to the chance. If I were to put these all to 50%, let's put even these hats, and let's just see what happens with equal distribution to every part of every chance module. And we could go in and set up a variety more kind of coin tosses here. We could set the amount in the Euclidean rhythm. We could say, well, we've got an 11, why not do, in fact, let's do that here. Let's take another one of these instances and bring these down here. And we'll say, what is that? We've got 9 and an 11. Okay. And let's swap that to be our input. And we'll use the 16th note to trigger that as well. In fact, no, what are we using? We're using a Euclidean rhythm as its trigger. Let's try that. Quite interesting. Of course, none of these notes are going through. What we could do is use that to be the chance that a note will go through. Quite interesting. Or maybe we use that to be the chance for the gate to come through on here. Because that means that we're only getting notes playing on the melody when the bass isn't playing. Let's bias this more to change note. We could use that as the input source. Anyways, the world really is your oyster when it comes to doing this. And what's quite fun is to start with something very simple and say, okay, what are the 2 options from this point? So as we did with the hats, for example, well, one of the options is we can either play 16th notes or 8th notes. So you start with that and then you move on to, okay, now we've got our gate signal. That gate signal can either play a short hat or a long hat. What next? Okay, so we're on the short hat. That can either play a short, tight short hat or a slightly longer short hat. And you could really then move on to say with the filters as well. I'll get the filter being at 6,780 hertz or at 5,000 hertz. And you can really build off of there with these very simple either or situations that then really start to build up over time. And of course, you could then take some sort of LFOs set to quite a slow speed. Let's set this to like 8 bars. And we'll do 1 to 7 bars and 1 to 6. And if you were to then map the probability of these things, if you set these to plus and minus, if you were to then map the chance of these things changing, you get some really interesting things happening. Obviously, these may be a bit too fast, a bit too slow, sorry. Or you could swap these with sample and hold LFOs. And you're then basically taking what are quite defined parameters, but then saying within those parameters, change them over time. Well folks, that's sadly all we have time for today, but I do hope that this video has been useful. If you enjoyed it, then please remember to like and subscribe and smash that notification button if you'd like to keep up to date with all of my future videos. I'd also like to take a quick moment to thank all of my patrons. Your support means the world to me. I am also, as I've mentioned before, a Bitwig certified trainer in case any of you would like one-to-one tuition. And in the meantime, I am now, as of the suggestion of Giorgio Martini, making my very own Bitwig grid course that you'll be able to access on Thinkific. So watch this space, that should be ready in the next month or two. Anyways, happy Saturday chaps and happy creating.